Hi everyone, so today we're going to have a look at collision theory. So for a reaction to take place, two particles need to collide. And they need to collide in the right orientation and with enough energy to break the bonds. So we need particles to collide. We need them to have enough energy. We also need them to be in the right orientation. Okay. Now, the activation energy is the amount of energy required for the reaction to take place. It's the minimum amount of energy required. Okay, so for a reaction to happen, they have to collide with this, at least this amount of energy. Okay, and we use the abbreviation EA. Okay, and so for a reaction to happen, the activation energy must be less than the energy of the particles when they collide. So over on the right, you can see this reaction energy profile diagram. Okay, this energy profile diagram, and you can see that the reactants have to gain a certain amount of energy, and we call that the activation energy. That's why it's written here. To be able to reach their transition state, that's where the bonds are broken, they're ready to react, and then eventually they'll become the products. Now this one here, where the reactants have more energy than the products, is an exothermic reaction with quite high energy activation energy here. There are several factors that affect the rate of a chemical reaction, okay, and they are, and you should know these hopefully, temperature, pressure, concentration, surface area, and the use of a catalyst. Now we're going to talk a little bit about each of these as we go through the next few slides. But you need to know these five factors that affect the rate. Make sure to note these down, and I will ask you to try and remember them in a minute. So the effect of temperature on rate and collision theory is really twofold. So increasing the temperature increases the rate. Now if we link that to collision theory, it kind of becomes quite apparent why it's so important. The temperature is so important because increasing the temperature increases the energy of the particles, and it increases the kind of the rate, the speed that they are moving at, which increases the number of collisions. So there is a much greater chance of having a successful collision if the particles have got more energy and they're colliding more regularly. There is a higher chance of those collisions that are happening being successful. Make sure to make a few notes before we move on to the next slide. I've put concentration and pressures together because they are very similar. Concentration, we're obviously talking about solutions, and pressure, we're talking about gases, okay? But they have the same effect, and the effect really is that by increasing the concentration or increasing the pressure, increasing the concentration of a solution or increasing the pressure of a gas, what we're really saying is happening is that there are now more particles in a smaller volume, or in the same volume perhaps if you're just increasing the concentration. Therefore, if you've got more particles in a smaller volume, therefore we should expect the number of collisions to increase. Now we haven't had any effect on the energy here, but because there are more collisions, the chances that there are more successful collisions are higher, and therefore the rate increases. increasing the pressure would have the same effect in a gas. Okay, so you'd be forcing the particles into a smaller volume, so there are more likely to be collisions. So the same effect. Surface area, so increasing the surface area increases the rate, and really we're talking about solid reactants here. We're talking about solid reactants. Now, it's slightly counterintuitive often, people find, because when we talk about increasing the surface area, a powder has a higher surface area than a lump or a rock of a solid, and that's because they're smaller pieces, and these diagrams on the right try and show you that. So we've taken the same square, we've cut it into 4 pieces rather than the original square. Now to start with, it only had this area here, so let's call that 2, and let's call this 2 units, centimeters perhaps. Okay, we cut it into 4. Now each of these has got a surface of 1. Okay, now I think here you've got 2, 2, 2, and 2, 2, and 2. So overall, the surface on that square, if we just count the perimeter, the surface on that square is 8. Whereas, if we were to look at the one down here, each of these little squares has got 1, 1, 1, 1. That's 4 for the perimeter of that square, 4 for the perimeter of that square, 4 for that one, 4 for that one. So actually, these smaller squares, where they've been cut down, have got a surface area of 16, as opposed to that 8 that there was originally with that square. So actually, smaller particles have a larger surface area. Now, for the same reason, similarly to concentration, increasing the surface area, breaking down this square into this smaller square, would increase the rate of reaction, or increase the rate at which the reaction happens. And the reason for that is an increased surface area leads to more collisions and therefore, okay, a higher rate of reaction. I'm going to talk very quickly about catalysts today, and I'm going to do a separate lesson on catalysts at a later date for a bit more detail. But really, a catalyst works, or to start with, what is a catalyst? Well, a catalyst is a substance that can change a chemical reaction without being chemically changed itself, or a substance that increases the rate without being used up. And the way it does that is it provides an alternative reaction pathway. And that alternative reaction pathway results in the same products at the end, but the key thing about that alternative reaction pathway is that it has a lower activation energy. So over on the right, you can see that you've got the activation energy without a catalyst, which is this taller of the two curves, and then we've got the activation energy with a catalyst, which is the smaller of these two curves. So you can see the activation energy required with a catalyst is much lower than the activation energy required without a catalyst. That means that when the particles do collide, they are more likely to have enough energy, so their energy is more likely to be greater than the activation energy with a catalyst, and therefore it's more likely to be successful collisions. So attached to this lesson there are a couple of exam questions for you to have a go at on Google Classroom. I'd like you to have a go at those now, and I will go through the answers with you afterwards. So pause the video now to go through those questions, and then I will go through those questions for you on this video. So here's the first question. Figure 1 shows the volume of hydrogen gas collected when a sample of magnesium reacted with excess dilute hydrochloric acid. The rate of reaction can be studied by measuring the time it takes for a given volume of hydrogen be collected. State the meaning of the term rate of reaction. And we've got a graph there as well. So this is green pen work for marking your work. State the meaning. So I'll just change to a green pen. State the meaning of the term rate of reaction. Okay, so the rate of reaction is the change in concentration, in this case, or in any case, per or in a unit time, as in a set time. So per second, per minute, per hour. Your rate could be in any of those. Change in concentration, change in volume. Essentially, it's the amount of substance formed or used up in a given time, or per a specified unit of time. So if you make sure you have a copy of the graph in front of you so you can have a look at this, but essentially the shape of the graph was a curve that flattened out at point W, or just afterwards. Point W was on the flat part of that curve. So what did that actually mean? Well, the first thing, stay and explain what has happened to the rate of this reaction at point W in figure 1. Well, if the volume of hydrogen is no longer going up and the time is continuing, so the volume of hydrogen is no longer going up, but we're still progressing in time, well, the reaction has essentially stopped. The rate is 0. Because, and this is why the explain part, so the statement is the rate is 0, the reaction is stopped, and because essentially needs to be because all of the magnesium has reacted, so it's no longer there. All of the hydrochloric acid has possibly reacted. Essentially, something that says there is no more reactions or collisions between the acid and the magnesium. The reaction is complete, or the reaction has stopped. And the most likely reason for that is that one of your reactants has run out. In terms of collision theory, explain why, at a fixed temperature, the rate of this reaction doubles when the concentration of hydrochloric acid doubles. Okay, so we're not messing with the temperature, but if we double the concentration of hydrochloric acid, we've got twice as many particles or molecules of hydrochloric acid, so twice as much. Twice as much HCl. Okay, and if we've got twice as much HCl, then we would expect, or twice as many molecules of HCl, we'd expect there to be twice or 2 times as many collisions, and therefore twice as many successful collisions. Collisions with the activation energy, or sufficient energy. Mark those 2, and then we'll do the next one. Okay, so in a study of reaction in part A, a student referred to activation energy. State the meaning of the term activation energy. Well, the activation energy is the minimum energy required for a reaction to begin. Okay. Complete figure 2 by drawing the shape of the reaction profile from reactants to products for an exothermic reaction. Show the position of the products, show and label the activation energy. So exothermic energy is being released to the surroundings, so the reactants is going to have more energy than the products, so we only need a line for the products further over in time, and it's going to be below the reactants, and you might want to label that. You should label that products. I'm just going to put a P. And then we know that we have to put in a little bit of energy to start. We have to reach that activation energy. So the curve starts by going up and then comes down. Your curve will be much neater than mine, because mine is being done on a tablet. I can't do that now. Okay, so The activation energy, essentially, you draw a dotted line across the reactants up to the top of your curve, the very top point. That is the activation energy. Remember, we label that with a capital E and a subscript A. That's your activation energy. So you get 1 mark for your products down here, and you get 1 mark for your labeling of your activation energy. I'm sure your drawing will be much better than mine. I'm not sure how much Group 2 chemistry you've done with Miss Clark yet, but this is part of the question. I thought we could go through it anyway. So write an equation for the reaction of barium with water. Well, barium, Ba, reacts with water, and it reacts with 2 water molecules to form barium hydroxide, which I will do my best to write, Ba brackets OH2 and some hydrogen gas. Okay. A solution containing barium ions can be used to show the presence of sulfate ions in an aqueous solution of sodium sulfate. Write the simplest ionic equation for the reaction that occurs and state what is observed. So it's the simplest ionic equation like we've talked about earlier in the year. So Ba2 plus, it's in group 2, plus the sulfate ion, which you should know is SO4 2 minus, make barium sulfate, and because it's 2 plus and 2 minus, it's just 1 of each of the ions that react. Now your observation should be that you would see a white precipitate formed. So state 1 use of barium sulfate in medicine. Explain why this use is possible given the solutions containing barium ions are poisonous. Okay, so the use for barium sulfate in medicine is during X-rays, and it's used as a contrast material. So essentially you swallow some barium, and it's used as an X-ray contrast medium. And the reason that you can use barium sulfate but you couldn't just use barium is because barium sulfate is, here we go, barium sulfate is insoluble and therefore non-toxic. So on to question 2, and this involves drawing a lot of curves on graphs, so I'll do my best to make them as clear as I can for you. So draw a curve on figure 1 to show how the total volume of oxygen collected will change with time if the experiment is repeated at 298 Kelvin, so same temperature, using 100 centimeters cubed, so same volume, of 2 molar per decimeter cube solution of hydrogen peroxide. So actually the concentration has been doubled. Okay, so we'd expect it to start at the origin. At the beginning there was no oxygen, so that would still start at the origin. But if we've doubled the concentration, or we've increased concentration, we would expect the rate to increase. So we'd expect a steeper line at the beginning. So I'm trying to start from 0, 0, and we would expect a steeper line. Now, before I finish my line off, we also need to think about how much oxygen is going to be produced. Well, if there's 2 times as many moles of hydrogen peroxide in the same volume, then actually you've still got more molecules of hydrogen peroxide that are going to decompose. You've got twice as many. So to start with, this one plateaued off at about 1.5 volume centimeters cubed, perhaps, if this is going up in 1. So if we're doing twice as much, we should find that actually it plateaus off at the top at the 3. Okay, so that is our second curve. So it should be going up. I'll make the line a little bit thicker so you can see. It should be going up from the origin up on a steeper curve. That's your first mark, and then it should plateau off around the top line of the graph. So see how you did there. So there's a mark for the steeper and it's a mark for plateauing at the top line. So a very similar question, but this time they have reduced the concentration to 0.4 moles. If you got the first one incorrect, pause this video now and have a go at this one. See whether after doing that first one that's helped you understand this one a little bit better. But if you want to have a go at marking it, we'll go through it now. So it's got a lower concentration, so the rate is going to be lower, so the line should be less steep. Start from the origin again, but it should be less steep. And it's going to produce 2/5 of the amount that it produced previously. So that's somewhere around the first line. So if I draw that line on, I start at the origin, and it's going to be less steep, and then it's going to plateau off around the first line on the graph. Okay, so less steep at the beginning, and then plateauing around the first line. So again, a similar question, figure 3, and this is all from the same question in A-level. You see each of these graphs have been worth 2 marks. It's a lot of marks available for this. So draw a curve on figure 3 to show how the total volume of oxygen collected will change with time if the original experiment is repeated at a temperature higher than 298 Kelvin. You should assume that the gas is collected at the temperature of 298 Kelvin, okay? So if the temperature is higher than 298 Kelvin, so the temperature has increased, then we would expect the rate to increase as well. So we're expecting it to be a steeper graph, starting at the origin, but being steeper. But actually, the volume of hydrogen peroxide is the same as the first experiment now. So if it's the same as the first experiment, and it's the same concentration, the same volume, then it should produce the same amount of oxygen. So we're expecting a steep line that plateaus off at the same kind of area as R. So a steeper line then plateaus off and follows along with R. Okay, so 1 mark for the steeper at the start because of higher temperature, and 1 mark for realizing that actually the volume of oxygen produced isn't going to change because the concentration and the volume of hydrogen peroxide is the same as it started as. So here I want you to explain, why does the gradient of the curve decrease as time increases? Well, it's really asking you, why does the rate of reaction decrease as the time goes on, as the reaction is carried out? Well, at the start you have more hydrogen peroxide, so the number of hydrogen peroxide molecules, or the concentration or amount of, any sort of way of saying amount of, the concentration of hydrogen peroxide decreases. Okay, therefore there are less successful collisions, or collisions are starting to decrease, the number of collisions is starting to decrease, and therefore less successful collisions, so the rate of reaction decreases. Okay, so the last question. The student discovered that hydrogen peroxide decomposes at a faster rate when a few drops of aqueous hydrogen bromide are added to the solution. The student found on the internet that this decomposition is thought to proceed in 2 steps as shown by the following equations. Step 1, H2O2 plus HBr makes HBrO plus H2O, and HBrO plus H2O2 makes H2O2 plus HBr. Write an equation for the overall reaction. So putting these two together, getting rid of any essentially spectator ions or any intermediates. So actually what we should find is that 2H2O2 forms 2H2O plus O2. Okay. Give one reason other than the increase in the rate of reaction why the student was able to deduce that hydrogen bromide behaves as a catalyst in this 2-step reaction. And the key thing here is, when you look at the overall reaction, that hydrogen bromide doesn't appear in the overall reaction. So it can't be part of the reactants. It is there, it's being used as a catalyst, it's not being used up. So it's not in the overall equation. Okay, fine. So hopefully this helped bring together some of the stuff that you guys were doing for me over Easter. You'll find I'm going to try and get better at doing these recorded lessons, and we'll see how they go. Let me know how you did on the questions in the comments, please. And let me know if I can do anything else.